Imagine a laboratory cloaked in darkness. In the center of the room, a series of delicate glass tubes begins to hum with energy. Close up, a coiled glass tube glowing with a bright pale blue-white light against a black background. A soft, ethereal glow fills the space, casting long shadows that dance on the walls. The light is a brilliant, almost ghostly blue-white. It feels otherworldly, like something pulled from the pages of science fiction. Distant galaxies, advanced alien technologies, and perhaps even the legendary home planet of Superman. The name Krypton itself is forever tied to these grand mythic stories. The popular image of Krypton is powerful. It's a name that conjures up weakness for a superhero or the remnants of an exploded planet. But the truth is far more subtle and in many ways far more fascinating than the fiction it inspired. The real Krypton is not a solid mineral from a distant star system. It is an invisible gas, a fundamental component of the very air we breathe every single day, hiding in plain sight. It's surprisingly ordinary and extraordinary at the same time. The discovery of Krypton was not a sudden, explosive event. It was the careful, methodical work of two brilliant chemists, Sir William Ramsay Morris Travers. The year was 1898, a time of immense scientific excitement. They were on a quest to map undiscovered elements of the periodic table, specifically a new family of gases they suspected existed. They had already identified neon. Neon would later light up cityscapes around the globe. They started with a large volume of air, cooled it to an extremely low temperature until it became liquid. And this liquid air was a cocktail of different gases. The process was fractional distillation. As temperature rose, different components boiled off at different points. They collected the familiar gases, nitrogen, oxygen, argon. After known components boiled off, a tiny, mysterious residue remained. They passed a high-voltage electrical current through the tube. The gas inside began to glow. Krypton belongs to a very special and exclusive group on the periodic table, the noble gases, helium, neon, argon, xenon, radon. What makes these gases noble is their chemical aloofness. Their atoms have a full outer shell of electrons, which means they are incredibly stable and content on their own. They show almost no desire to react. This property, known as being chemically inert, makes them safe and predictable to work with. In its natural state, Krypton is completely unremarkable to our senses. It is a colorless, odorless, and tasteless gas. Its presence is defined by its absence of interaction. Krypton makes up only about 1 part per million of the Earth's atmosphere. When a high-voltage electrical current is passed through a low-pressure tube of Krypton gas, as they return to their stable state, they release that extra energy in the form of light. The light produced is a brilliant, smoky white with hints of blue or lilac, a stark contrast to the brilliant orange-red of neon or the soft lavender of argon. So, quiet, reliable, and oddly essential. Obtaining a usable amount of Krypton is a significant industrial and engineering challenge, primarily because it is so thinly spread throughout our atmosphere. The process all begins with the air around us, but it requires massive facilities known as air separation plants. The first step is to collect enormous quantities of air and filter out dust, water vapor, and carbon dioxide. This purified air is then compressed and cooled to cryogenic temperatures until it condenses into a liquid. This liquid air, a pale blue fluid, is a mixture of all its constituent gases. The next stage is the heart of the operation, fractional distillation. The liquid air is carefully pumped into a tall distillation column. As it is gently warmed, the different gases begin to boil at their unique boiling points. Nitrogen, argon, oxygen. As nitrogen, argon, and oxygen are removed, a small concentrated liquid remains at the bottom of the distillation column. This liquid is a crude mixture rich in krypton and xenon. This mixture must then undergo further, more refined stages of distillation to separate the krypton from the xenon and any remaining traces of other gases. Because krypton constitutes only about 1 part per million of the air, the sheer volume of air that must be processed is immense. This is what makes krypton so much more expensive than argon. Despite its rarity and high cost, krypton's unique properties have carved out important niches in modern technology. One of its most visible applications is in high-performance lighting. Krypton is used to fill certain types of energy-efficient incandescent light bulbs. Because krypton gas is denser than the more common argon, it slows down the evaporation of the tungsten filament, allowing a higher temperature, producing a brighter, whiter light, extending the bulb's lifespan using less energy. This is why, krypton bulbs were often marketed as a premium, long-lasting option. Its ability to produce intense, short bursts of brilliant white light makes krypton essential for high-speed photography. The flash lamps used by professional photographers are often filled with krypton or a krypton-xenon mixture. When a powerful electrical charge is sent through the lamp, the gas ionizes and releases an incredibly bright and instantaneous flash, capturing moments that would be a blur to the naked eye. Krypton gas is also a critical component in certain types of lasers. In a krypton ion laser, the gas is the lacing medium, producing green, yellow, and red wavelengths. These lasers are used in scientific research, for medical procedures, in entertainment for light shows. Furthermore, krypton plays a vital role in airport safety. The bright, penetrating white lights used to define airport runways and taxiways are often krypton-filled lamps, ensuring pilots can see clearly in fog or heavy rain. To truly appreciate krypton, it helps to see it in the context of its noble gas family. Each member has a distinct personality and role defined by its abundance, atomic weight, and light signature. Neon is perhaps the most famous. Its iconic, brilliant reddish-orange glow has made it synonymous with city, nightlife, and vibrant signage. Argon is the dependable workhorse of the group. It is the third most abundant gas in our atmosphere, cheap and widely available. An inert filler gas in bulbs and a shielding gas in welding. Argon is the practical, everyday gas, while krypton is the high-performance specialist. It shouts where krypton whispers. Xenon is the heavy, powerful, and even rarer sibling, denser and more expensive than krypton, producing an extremely bright, pure white light closer to natural daylight. If krypton provides a bright flash, xenon provides a sustained, brilliant beam. Krypton, therefore, occupies a unique middle ground, rarer and more expensive than argon, but more common and less costly than xenon. Its glow is a cleaner white than neon's red and less intensely blue-white than xenon's. This just right positioning allows it to be the optimal choice for specific tasks. The story of Krypton is a perfect example, once completely hidden from us, revealed and woven into our technological world. From a tiny residue in a London laboratory, lighting, science, safety, it helps us save energy in our homes, capture fleeting moments with our cameras, navigate our world more safely. For much of its history, Krypton has been misunderstood. Ramsay and Travers unlocked a new tool. Today we find new uses in lighting, measurement, detection. Looking forward, Krypton's role will evolve. Perhaps energy-efficient windows will become more widespread, or new lasers, new medical devices relying on Krypton's unique spectral lines. The future is unwritten. The story is far from over. Krypton was once hidden from the world. Now it helps light our cities and power scientific breakthroughs. But as new technologies emerge, what role will this mysterious noble gas play in our future?